Hello and welcome back to another video. Today we're going to be working on lowest common ancestor of a binary tree 2. So in this problem you're given a binary tree and you want to return the lowest common ancestor of two given nodes P or Q. And I'm going to show you what this is going to look like in these examples essentially. So let's go through number 1. So we have a tree here, 3, 5, 6. And this is not a binary search tree, this is just a normal binary tree. 7, 4, 1, 0, and 8. And so let me actually draw this in a different color just to give you some intuition. So here we have nodes 5 and 1, right? So here's node 5 and here's node 1. So essentially what you need to do is you need to find like the first ancestor of these two nodes. So in this case it's actually going to be the root, right? Like the node that connects them. Okay, so it's going to be the root in this case. It's the first node that like their path interacts at. So that's going to be that for that one. Now we have another one, and we have two different nodes. So we have 5 and 4. So here's 5 and 4. And two nodes can be on the same path. So if you actually go up from 4, you hit this 2 node, and then you hit this 5 node. And now this 5 node is the lowest common ancestor because both of these nodes are on this path, right? So that can happen. They can be on the same path, and they can also be on different paths. So for example, if we had like 6 and 2, their lowest common ancestor would be this 5, and now I think you should be getting the hang of it. You know, if we had 6 and 4, their lowest common ancestor is this 5. So it's essentially like if you draw a path from both of these nodes to the root, then it's going to be like what's the node that they first hit that's the same node, right? So let's go to the last one. So the last one is going to be 5 and 10, and 10 doesn't actually exist in here, so we need to return false. So like I said, what you need to actually be doing is you need to find the two nodes, and you need to figure out like what node do they intersect at. And there's going to be a few scenarios, right? They're either going to be on like, they're either going to intersect somewhere, or they're just going to be on the same path, right? With this like 4 and 5. And so we need to find how to actually do this. And ideally, we wanted to be able to do that in linear time. So how do we actually do this? Like, how do we traverse a tree? And what do we want to return? Or, you know, like to figure out what are our nodes? So let's go for this example, this 6 and 4 example, right? So we have node 6 and we have nodes 4. And we want to figure out how do we traverse a tree and figure out the first node they intersect at. It should be this node 5, let's say for this example, right? So how do we actually do that efficiently? Well, what we can actually do is we can just traverse down and we can just say, like, if we find one of the nodes, we can return some value. And then we can just check. So for every node, there's going to be a left, right? There's going to be a left, a right, and the node itself. Let's just call that maybe node, right? So if you think about it, for two nodes to connect at a path, that means that two of these have to be true. Either the left and the right, or the right and the node, or whatever. And let's take a look at some examples here. So let's actually go back to this. Let's go back up here. So we need the 5 and the 1, right? So we're gonna go up here, and you can see for this node 3, the left and the right are both a node that we care about. So the left and the right are true here. And then let's look at the 5 and the 4. So the 5 and the 4, once we go back up to this 5, right? For the 5, the node and the right are nodes we care about, right? We're going to pass up, like, we're going to pass up some value. So the node and the right are nodes we care about. So essentially, this is what we're going to be doing. So what do we actually want to be returning, right? So we're going to have some result. We're going to set it equal to null. Just to start off, right? We're going to set it equal to null. And then what do we actually want to be doing? So let's see what this is going to look like. So we actually are going to start at node 3. We are going to, let's just say we go left first, then we go right or something. So we're going to go here, okay? Then we're going to go here. Now this node, we're going to go to a child, right? So we're going to go to the child and the other child. And let's just return, we just want to know if a node we traversed actually contained a value we care about. So what we can actually do is we can just return false if it doesn't. So like for this node here, we can just say like, okay, for the left child, if the node doesn't exist, let's return false. So this left child will return false. We're going to traverse down to it. It's going to return false. We're going to go to the right child. We can return false. You could also skip this check. You could just say like if the node's children don't exist, return false. That's fine too. And now what we're going to actually do is for the node itself, we're going to say if the node is equal to one of these values, then let's return, or let's set that node equal to true. So for example, for node 6, what's the left and the right going to be here? So the left is going to be false, the right is going to be false, and the node is going to be true, right? It is a node we care about. And then finally, what we need to do is we actually need to return saying that we found, like we either found one of these values or we didn't. So we can just return, if any one of these is true, let's just return true. So for 6, we're actually going to return true up to 5. So we're going to return true here. Now we are at 5. We want to go right now. So we go right. And now remember, we go left first. So we go left here. Okay, so for this node 7, what is this going to do? Let's delete all these. For these node 7, the left is false, right? Because there is no left. The right is false. And for the actual value of the 7, it's not a node we care about, so it's going to be false. The 7 is going to return false up to this, so we're just going to write it up here. It's going to return false. Okay, what about 4? Right, we're gonna recurse back up to 2. We're going to go to this right child over here. So what about 4? The left is false because there is no left. The right is false, and the node is true. So here we're going to return true. So now let's go back up to this 2. What do we need to return? So if either the node or one of the children is true, we're going to turn true. So we're actually going to return true here. And now when we're up here, so for this true, by the way, before we returned, we need to check the left, the right, and the node, right? So for the left, the right, and the node for this 2, so the left is false, the right is true, and the node is false. Right? So we need 2 of these to be true to have a valid node. So here we're going to return false. Now we go back up to this 5. Okay, let's take a look. So sorry, actually, for this true, we need to return true, right? Because any one of these needs to be true to return true, but 2 of them need to be true for it to be our lowest common ancestor. So here we're actually going to return true. So now for the 5, the node is false, the left is true, and the right is true. So here, actually, we do have 2 of them being true. So if 2 of them are true, that is our lowest common ancestor, because that means we ran into both of these nodes, right? We were looking for 2 nodes and we found them, and this is the first place that we found them. So here, we're going to update this result to be the 5, right, essentially. We're going to delete this null, and we're going to say, okay, our result is 5. But how do we prevent ourselves from overriding this result? So it's pretty straightforward. We're just going to return true here, right, because only one of these needs to be true in order to return true. So this 5 is going to return true. Now for this, we're going to go over here, and then we're going to go over here. So for the 0, obviously none of them are true because, for the 0, it's going to be false, 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 right? False, false, false. Because it doesn't have a left or a right, and it's not a value we care about, so that's going to be false. Same thing for the 8. I'm not going to write that out, but for the 8, it's also going to be false, false, false. So this is going to return false, this is going to return false. Now this 1 is also going to return false because it's not a value we care about, and the left and right child aren't either. So that's going to return false. Now this, we need to make sure that like somehow we don't override. So, and the nice thing is because we're only returning 1 value, there's only going to be 1 node that's going to have 2 true values. So this node had 2 true values sent into it, right? Because the left and the right were true, but the node was false. But when we return, we're only returning 1 true value. So now for this node 3, when we actually look at it, the left is true, the right is false, and the node is false. So there's only going to be 1 spot in the whole tree if you're just returning like this, that 2 of the values are going to be true. And so here, this is going to return true, but it's not going to override our result. So let's actually write down our steps, just so we can make sense of it. So traverse the tree, right? Recurse left, then recurse right. Then if 2 of the values from left, right node are true, then update result to be that node. Finally, return true if left or right or node are true, else false, right? So that's what we're going to be doing, and there's only going to be one node in the tree where this is going to be true. And that's going to be this node here for this example, but it's always going to be the case for this for any kind of problem, because you're going to have one node with 2 true values, and then we're only going to be returning 1 true value. So we need 2, we're only going to be returning 1, so there's not going to be any other node that's going to be true. Or sorry, it's not going to have this condition of 2 nodes being true. This condition here, right? Okay, so that's our algorithm. Traverse, traverse left, traverse right, and then if any of the values from the left or the right are true, you need 2 of them. You need 2 of them. So if 2 of the values need to be true, that means we found our lowest common ancestor. Okay, so now we have enough to code this. So let's just say we can just make a variable that we're gonna use later on. So we could just say like non-local, or we don't need to do non-local. We can just say result. We're gonna set it equal to null initially, and that way, if we don't find a lowest common ancestor, we're gonna be returning the result, but we would have never have updated it. Okay, so now let's make a helper function, and that's just gonna take a node. And so if not node, that's like if a node is an empty node, we're just gonna return false. Okay, now we're gonna make a, this is not spaced correctly. Okay, so now we're gonna say, let's go left. So left equals traverse node.left, then right equals traverse node.right. Now finally we need to check. So we can just say value, right? So let's get the value of the node. So we can say value equals 1 if node.val equals p.val, or node.val equals q.val, else 0. So actually we want this to be true or false, right? So false and true. So we're essentially saying if the value of the node is equal to one of these, then the node is a node we care about. Otherwise, it's not. Okay. So now we need to check, do we have 2 of these? So we can just say if left, and you can actually add booleans and it'll just treat it as 1. So you can say if left plus right plus val equals 2. Right? If 2 of these are true, then let's update this result. So we can just say non-local result because it's not in the scope of our function. So we can't. So we can read it, but we can't change it unless we do this non-local, or you have it be like a class variable. You could say self.res. There's a bunch of ways you could do it. You can also make it an array with like one element. But yeah, so now we're just going to say res equals this node. So we're going to say node, and then finally, what are we returning? We're going to return node. We're going to return val or left or right. Right in the picture, if one of these is true, we need to be returning true. Now we're going to call traverse on the root. And then we should be able to return the result. And let's see if we screwed anything up. Probably did, but let's take a look. Okay, so this should be none. Node. Okay, so you can see it's really efficient and it does work. So let's actually go through the time and space complexity. So for time, we're just doing a standard traversal, right? We're doing a, I guess this would be a post order traversal. We're checking the left, we're checking the right, and we're checking the root. So that's just a little event traversal. Yeah. For space, so this tree is not guaranteed to be, once again, for all these tree problems, usually trees aren't guaranteed to be balanced, right? So we can have something like, just delete this for a second. So let's say our tree looks like this, right? That means we need to maintain a recursive call stack of all of these nodes. So worst case scenario, our whole path is just like this. And then we need to go through this whole tree. So then this would be big O of n complexity because you need to maintain a call stack of every single node as you're going down. But for a balanced tree, so you could say this, like if you were asked on an interview, you know, what would be the worst case space and what would be the average? The average would be like log n if the tree is reasonably balanced, because then you're cutting off half the tree every time, and then you're only going log n down. So for a tree of, 9 nodes, or what, not 9 nodes, for a tree of 8 nodes, you would only go down like 3 levels, right? So like this tree right here is, not counting this part, is 7 nodes, and you're only going down to the 3rd level. So that's going to be the way it is. Okay. So that's actually going to be it for this problem. Hopefully you liked it. I definitely think it's a good one to know. I think it's a pretty common interview question, so I definitely make sure you know it. And if you did like this video, then please leave a like and subscribe to the channel. And I will see you in the next one. Thanks for watching.